Hi, and welcome to this next video on learning theory, where we try to give some justification for the learning algorithms that we've seen so far, and why it's actually reasonable to believe that training a machine learning model to perform well on the training data also leads to models that perform well on new data. Okay, so let's start out with just the basic question, right? When you say that we want to train a machine learning model that can learn how to perform well on new data, maybe we should start by asking ourselves whether this is even possible, right? Can we even hope to train such a model and hope that the performance on the training data carries over to new data, right? And in particular, what type of theoretical guarantees can we give on the quality of the model that we train? Okay, so let's try to have a look and just recall what we're the supervised learning setup. So the basic setup is that we're trying to learn some unknown target function f, right? So and what we have available is training data. So the training data again consists of these training examples where we know a feature vector x1 and the corresponding label f of x1, so the evaluation of the unknown target function on this feature vector. And we have n of these pairs, which consist of a feature vector and a label, which is an evaluation of the unknown target function on this given feature vector, right? And the goal again was that we want to try and learn a hypothesis H, which is close to this unknown target function. So hopefully it should give the same predictions. It should predict the labels assigned by the unknown target function correctly, also on data that we haven't seen yet, right? And the way we're going to do it is that we're going to look at this training data that we've collected and then use this to guide the search for such a hypothesis, right? So maybe if we look at this data here, right, a natural hypothesis to choose would be the one that you see on the line here. However, right, this is only the training data that we have available. We don't know what the future data will be, and perhaps some of the data looks like this, right? So you actually are going to misclassify some of the blue points here. Right? There's some blue points on the wrong side of this hyperplane that you chose, basically because you didn't have all the data available when you were training. Right? So of course you cannot pick a perfect one, but at least this H is pretty good at classifying. Right? And maybe this is actually the true hypothesis if this is the actual unknown target function that assigns a label of blue to everything on the left and a label of red to everything on the right. Right. So we're using this training data that we have here to guide the search for a hypothesis that is close to this true unknown target function. Right. Of course, the unknown target function doesn't necessarily have to be a hyperplane, right? It can be anything. This is just for example. Okay. So of course we should ask yourself, right, what do we really mean when we say that the hypothesis is close to the unknown target function, right? And basically what we're after is, of course, that this hypothesis that we trained makes few mistakes if we ask it to classify new data, right? That's the whole goal of it. We want to be able to classify new data that we haven't seen before. Okay, so this is what we mean by being close, right? And of course, we should start asking ourselves, is it even possible to use training data to find a hypothesis that has small error on new data, right? So here's another picture of this situation we saw before, right? So the data comes from some set of all the possible d-dimensional feature vectors, and the training data gives you some of them, right? So maybe here on this picture here, let's say that we've seen the training examples x1, x4, x6, and x7, and we know that the labels assigned to them are 1, -1, -1, and 1. And now what we're asking is really, is it possible to find a hypothesis H, right, that is good at predicting the values here at the questions marks, right? Because these are basically the places we haven't seen yet, right? This would be the new data that was not in our training data. So is it reasonable to expect that we can predict these values solely by looking at the evaluations in the training set? Right. So maybe the first thing to ask ourselves here is like we kept arguing that it was a good idea to try and find a hypothesis that does well on the training data. Right. So, maybe I'm searching through my hypothesis set and then I find this hypothesis H. And of course, right, on all the training examples that we've seen, it perfectly classifies the training data. Right. So it gets it predicts 1 here, it predicts -1 here, it predicts -1 here, and it predicts 1 here. So it gets all the training data correct. And of course, this hypothesis H that we chose, it has to make some choice on the elements that we didn't see, right? So maybe it predicts -1 here, 1, -1, and -1. So we can ask ourselves, right, So is it always the case just because that we're correct on the training data, we will also be correct out here? Of course, the trivial answer is no, right? If f is truly unknown, right, we don't know anything about it, it can be any function, then of course it could also be the function that assigns exactly the opposite labels on the data that we didn't see as what h does, right? So in general, it's not the case that just because a hypothesis that we find looks exactly like the unknown target function on the training data, then it also looks like it on new data, on the unknown data. Right, so this is in general too strong a property to hope for. So of course we should then ask ourselves, what can we then aim for? Good. So what can we hope to prove? So it looks pretty bad, right, if we look at this example, because of course this unknown target function could just be the opposite on everything we didn't see yet. So we have to make some assumptions. So the basic strategy is that we're going to make some statistical assumptions about how the training data was obtained, right? And also how this training data relates to new data items, right? So in some sense, we kept saying previously that we're crossing our fingers and hoping that the training data is similar to new data similar to the training data. And now we're going to try and formalize that into a clear definition of what this means. Okay, so to do that, recall again the basic setup in supervised learning, right? There's this unknown target function f that assigns labels to feature vectors. And we see these training examples x1 to xn and the corresponding labels, and then we have to use this to produce the output hypothesis. Now, we're going to introduce another ingredient to this picture, and this is a data distribution which generates the data. Okay, so what we say is that there's some unknown input distribution D, and what D does is that it will generate the training example for us. It will also generate a new element x, the new data that we have to evaluate the hypothesis we output on this new data item. Okay, so let's try to be a bit more formal about it. But basically, we're going to try and say that there's some random process that generates the training data and new data. Okay, so let's see, what do we mean here? Right, so what we do is that we're going to say we assume that there is some input distribution D on feature vectors, right? And we don't know what it is, right? It can be any distribution, right? So we want to make as weak assumption as possible to prove the most general result. So basically, we're not going to assume anything other than the fact that there is some unknown distribution on input feature vectors. So it's a distribution over d-dimensional feature vectors, okay? And now what we assume is that the training data that we have was actually obtained by repeatedly sampling a feature vector from this distribution D, and then feeding that and the corresponding label as a training data item. And the assumption is that all these training examples are drawn independently from this data distribution D. Okay, so we assume that the data that we get, that we feed into our algorithm, was obtained by drawing independent random examples, training data points from this unknown data distribution D. Okay. And what we also do to assume, to make a connection between the training data and the new data, is that we assume that this new unknown data element follows the same distribution, right? So the new example that we need to classify is also drawn from this distribution D independently of the training data, right? Of course, the distribution could have a huge support. So think of it can be distribution over images, right? So of course, we're never going to see the same image twice in the training data, and we're not going to see any of the new data items in the training data, but we just assume that there is this unknown distribution that we don't know, and it generates data for us, right? It generates the feature vectors. And the new data we need to classify comes from the same distribution, right? And this really is what we mean when we say that this new data is going to be similar to the training data. What we really mean is that the new data was drawn from the same distribution over inputs. Okay, so actually this assumption is enough to get us going. Okay, so what we would like to prove now is that that when I get a new data point, right, I get an x from the distribution D. Then what we'd like to prove is that the label assigned by this hypothesis that we trained is equal to the label assigned by the unknown target function with high probability over this distribution D, right? Which means that basically if I get a new data item and it comes from this unknown distribution, then there's a high probability that I'm going to classify it correctly. This is the goal that we want to prove. Okay. So again, this is the setup. the unknown input distribution D generates n feature vectors independently that are all drawn from this same distribution, we see those feature vectors along with their labels assigned by the unknown target function. And then the final hypothesis, when we are to evaluate it, the quality of it, and we're hoping that on a new element drawn from the distribution D, there's a high chance that the hypothesis predicts the label of this X correctly. Okay, so let's try to introduce some concepts that we need in order to try and formalize this and prove something. Right. So the first thing we'll introduce is what's called the in-sample error, and we'll denote it by E sub n. Right. So the in-sample error is just the error on the training data. Right. So we call it in-sample because this is the sample that you hold in your hand. So the in-sample error. Right. Of course, the in-sample error, the training error, the number of mistakes you make on the training data, this is what we can try to minimize when we have a learning algorithm. Right. This is what the perceptron learning algorithm is doing. And this is also what these decision stumps and decision trees were doing. Right. They're trying to minimize the number of mistakes we make on the training data. Right. So we can minimize the in-sample error because here we have the data available and we know the labels, so we can check to see how many mistakes we make. And then, of course, there's what we call the out-of-sample error, E out. So this is the error that we make on new unknown data, right? So the chance of making a mistake when we get a new data item. And this is really what we actually want to minimize, right? If we could, we would like to minimize the out-of-sample error, but we don't know how to do it, right? Because we don't know the unknown data distribution. We don't know what new data is going to look like. Great. So the hope is that now, using theoretical arguments, that we can prove that the in-sample error of the hypothesis we produce of the machine learning model is close to the out-of-sample error, right? Because if we can prove this, then if we minimize the in-sample error and the in-sample error and out-of-sample error are close, then we're also going to minimize the out-of-sample error, right? This is actually the basic idea in machine learning, right? You're using the performance on the training data as a proxy for the performance on new data. You're minimizing the in-sample error, and then you're hoping that the in-sample and out-of-sample error are close so that you're actually also minimizing the out-of-sample error. Right. Good. So the in-sample error again. Right. So remember again, the input is d-dimensional feature vectors, and the labels come from some domain Y. What we also assume is that there's this unknown distribution D that generates input feature vectors. And then, of course, there's also the unknown target function, which maps the feature vectors to the labels. Right. And the input to the machine learning algorithm is these n samples where each xi is drawn independently from this unknown distribution D. Okay. And what we're going to look at for the error is we're going to use this 0-1 loss that we saw in the last lecture. So what we're going to define here is the in-sample error of a hypothesis H. So if we look at any concrete hypothesis that we've trained, maybe it's the one we output by our algorithm, then its in-sample error is just you average over all the training examples of this notation here, the indicator for whether the prediction made by H on the ith training example is different from the true label assigned to the ith training example. Right. So this notation here, the indicator with a Boolean expression down here, it just takes the value 1 if this Boolean expression is true, and it takes the value 0 otherwise. So basically, this is 1 if we make a misprediction on the ith training example, and it's 0 if we predict it correctly. Okay. So what we're doing here is really we're averaging over all the training examples of this indication for whether you mispredict the point. So all that this is doing is that you're summing up the number of mistakes that you make, and you're dividing by the total number of training examples. So this is just a fraction of mistakes that you're making. Right? So the fraction of training examples that you classify wrongly, this is what we call the in-sample error. Okay. Now, in general, the way we wrote this formula, you can also choose other loss functions that we saw in the last lecture, right? So if you have a general loss function L, the in-sample error is just defined as the average over all the training examples of the loss on that example, right? So here, the loss here is just the loss evaluated on the prediction made by the hypothesis H on that example and the true label of that example. Okay. So for the rest of this lecture, this video, and also the next, we're just going to focus on the 0-1 loss. Okay, so this is just to simplify matters. We're only going to deal with the 0-1 loss. And several pieces of the analysis we'll go through will only apply to 0-1 loss and not to general loss functions. Okay, Now, the second ingredient again was this out of sample error. Right, so recall again, right, we have the input domain, d-dimensional feature vectors, an output domain y, and an unknown target function, and this unknown data distribution d. And again, we'll use the 0-1 loss that we saw on the previous slide and also in previous lectures. When we define the outer sample error of a hypothesis, we just say this is just the probability where the randomness is overdrawing an example from this unknown data distribution d. It's just the probability that this hypothesis H mispredicts the label of the point X. Right, so it's just the probability of making a mistake when you see a new data item. Right? It's a very natural definition of the outer sample error. And you can also do general loss functions. Then it's not the probability here, but then it's just the expectation over an element X drawn from the distribution D of the loss function applied to the evaluation made by the prediction made by H and the true label of that element X. Okay, and actually you can see, so here down here it's an expectation, up here it's a probability. Actually, they're the same for the 0-1 loss. If you remember, the 0-1 loss is just the indicator that evaluates to 1 if the prediction y prime is not equal to the true label. So if you look at the expectation of the loss function, when the loss function is the 0-1 loss, as we have here, then if you know what the expectation of an indicator random variable, or in general, the expectation of a discrete random variable is the sum over all the values it can take. You take that value and multiply it with the probability of getting that value. So here, for an indicator random variable, right, the expectation is 1 times the probability that the variable is 1 plus 0 times the probability that it's 0. The 0 term cancels out, so there's just 1 times the probability that it's 1. And the 1 is just a factor 1, right? So it just equals the probability that the indicator random variable is 1, which is the probability, in this case, that you misclassify the point. Okay, so this, the probability of making a mistake is just the special case of this expectation down here in the general definition of the outer sample error when we plug in the loss function, that's the 0-1 loss. Okay, but it's a very natural definition of the outer sample error. Okay, so this again is what we're going to focus on for the rest of this lecture. So, okay, so let's go back to this picture again here, what we mean by this function H that this hypothesis that we found, that it looks a lot like F. Basically, what we want is that this hypothesis H has small error on new data, right? So what we really want is that the outer sample error of this hypothesis H is close to 0, meaning the probability over a new example that we predict a different class than the one assigned by the unknown target function is very close to 0. This is the ideal setting. We want to have as small as possible and out of sample error. Okay. Now, again, the problem is that we don't know what this unknown target function is, and we don't know what this unknown data distribution is, right? So we don't have any of those two available when we're trying to train our machine learning models. Good. So basically what we would like is we're searching for a hypothesis that have an outer sample error of close to 0. That is what we want. But what is it we have, right? What we have available to find this H is these training examples, right? We just have the n training examples, x1 to xn, with the labels f of x1 to f of xn. This is what we can use to guide our search for H, right? And then we also have this hypothesis set H, where we have to pick our little hypothesis from. Okay. So in general, right, the strategy that we've been looking at also in the previous lectures was to try and find a hypothesis in the hypothesis set that has a small in-sample error, right? One that makes few mistakes on the training data. And that's the strategy we've been following the whole time, and then we're just hoping that this means it will also perform well on new data, right? And the reason why we're hoping this is basically that we're hoping that the in-sample error of a hypothesis is close to the outer sample error, which then in turn will be close to 0. Right? That is the basic hope, that all of these terms are roughly the same and they're all roughly 0. Good. So for instance, H again could be all hyperplane lines, right? And we would search for H like this. Okay. So is it reasonable now, we could ask ourselves, is it reasonable to hope that all of these 3 will be 0 or close to 0? Right. Again, the unknown function F, we don't know it, right? And we only see the evaluation on some of these points, and we have to pick a hypothesis based on this. right? So similar to before, right? It still doesn't seem reasonable just because we added this random process that generates the training examples. It doesn't seem reasonable to guess these question marks without knowing what they are, right? If we don't know anything about F, how would we be able to guess these question marks, right? So we should ask, so what can we actually prove here, right? So maybe let's start by getting rid of this assumption that we're going to have a performance or an out-of-sample error of close to 0. Maybe let's just start by saying, okay, at least we want it to be the case that the performance on the training data, the in-sample error, is close to the out-of-sample error, right? At least if we can do that, then maybe we've gotten somewhere, right? So again, you can ask yourself, right, is it always the case if I find any hypothesis that the in-sample error is close to the out-of-sample error, right? So of course, this is not the case just by the same example here, right? If again, this is F is the unknown target function, you only see the black columns here. There's a hypothesis here that is perfectly correct on all the data that you saw, but it's completely wrong on everything you didn't see, right? So black is the sample that we see. Right, and in this case, right, of course, this hypothesis H had an in-sample error of 0, and you know, maybe we could just assume that this unknown data distribution just picks a uniform random point feature vector amongst x1 to x8. Then for this uniform distribution, right, the in-sample error is 0, and of course the out-of-sample error of this hypothesis is a half, right, 50%. As soon as you get one of those columns that you didn't see here, x2, x3, x5, or x8, the hypothesis H is going to misclassify it, right? So it seems that, you know, even though we introduced this distribution that's generating the data for us, it's still not clear, or it's definitely not always the case that if I pick a hypothesis that has a small in-sample error, then its out-of-sample error is going to be small as well. Right? They're not even guaranteed to be close. You know, so really, what can we say, right? What's going on here, right? It doesn't seem like this assumption about data being generated from this distribution D has helped us at all, right? So but there's one key observation here with this example that shows what is going on, right? So if we look at this example, right, I have a hypothesis H down here, and there's the unknown target function F. And if we look at these two, and we look at the out-of-sample error, right? So we know for this uniform distribution, H is wrong 50% of the time, right? So if I didn't already tell you which samples you got, right? If you're just drawing, if you look at these two, F and H, and I give you a training data set, right? So this would just be of, let's say, 4 elements. Then that would just give me 4 random points because it's the uniform distribution. And then in this case, it seems super unlikely that we would actually get this data set here, the black ones. If these two, F and H, completely disagree in a lot of locations, and you give me a training data set that we just pick uniform random training examples, then it should be super unlikely that you would actually end up with training data where H and F completely agree, right? In this case, right, you would have to always sample from the black part to have them completely agree. In general, right, if there's a 50-50 chance that you're wrong and you have n training examples, the chance that you never see a training example where H and F disagree is something like 2 to the minus n, right? It's just really unlikely that you would get exactly this black set of training examples if they disagree almost everywhere. So this is the idea and observation we'll be using. Okay, so what we will actually prove is that it is probably the case that the in-sample error is close to the out-of-sample error. Right, so let's try to say that. So with probably the case, what we really mean is that with good probability, over the data, the training data that we got, it will be the case that the in-sample error and the out-of-sample error are close. This is the kind of statement that we can hope to prove, right? So basically, right, if we look at the input space that we have our D, these are all the D-dimensional feature vectors. There's some random process D that generates a data set for us. And what we're saying is that, with the good probability over the generation of this data set, so when we get our data set, there's a good chance that any hypothesis that we would produce, any H, will have an in-sample error that's close to its out-of-sample error. And this is what we're trying to prove. In general, this is called packed learning, and this stands for probably approximately correct. right? So approximately correct means that the in-sample and out-sample error are close, and the probably is over the training sample, that it's only with good probability over the training data that this is the case. Okay. So this is the type of statement that's the best we can hope to prove basically by these arguments we saw before, right? That you cannot really hope to prove something stronger than this. Okay. So let's try to prove something like this, right? Let's try to actually argue that there's a good chance that the in-sample error and out-sample error are close. And we're going to start out slowly. We're going to start out by looking at what happens if the hypothesis set that we're using consists of just one hypothesis, right? So it's a much simpler setup. The algorithm basically has no choice. It always just outputs the same hypothesis. Can we, at least in this case, say that the in-sample error and out-sample error of this one hypothesis are going to be close? Right. So we want to prove that the in-sample error of H, this one fixed hypothesis, and the out-sample error of H are close with good probability over the random data set. Good. So let's try to see how we can make such an argument. So, okay, so I'm trying to visualize it here. So let's let this bag here represent all the possible feature vectors out there, right? And inside this bag, each of these marbles represent a feature vector that you could get, right? So the distribution D is over all these marbles. So these are all the possible feature vectors, and I've colored them red and green, such that the green ones are the ones where this fixed hypothesis H gets the label correct, right? So this is something, the hypothesis is fixed, the unknown target function is the unknown target function. So you can color these marbles red and green, right? The ones that are correct are green, the ones that you get wrong are red, right? So just from this one function, I can color all the possible feature vectors I get at input. I can partition them to the ones where we're correct on and the ones that we're wrong on. Okay, so now what is the outer sample error, right? The outer sample error is really the probability of getting a red marble, right? It's the chance when we get a new data item, a feature vector, that we'll misclassify it, and these are precisely the red ones. The red marbles are the ones that we misclassify. Because the probability of drawing any particular marble should be proportional to the data distribution D. But basically, the outer sample error is just the chance if I put my hand in the bag and I pick a red marble, right? One of the feature vectors that I misclassify. So that's the outer sample error. Now, what is the in-sample error with this analogy? Now, the sample itself, right? Recall that the sample is drawn by picking n independent samples from this unknown distribution D. So this just corresponds to sticking your hand in the bag and picking n marbles one at a time. And then a technicality is that this is with replacement. So if you draw a marble and you see that it's green, you put it back in the bag, right? And the same with the red, right? If you pick a red one, you actually put it back in the bag and just note the number of times that you drew it, right? Because it's the same distribution D that you're drawing from in each round. It's not like you cannot draw the same element again. So it's basically n marbles from the bag with replacement. Okay, so that's the data set. So basically you would get something like this, right? If you put your hand in the bag, maybe you'll draw, first you'll pick a green marble, a green marble, a green marble, then a red marble and a green marble, right? So now with this notation, the in-sample error, right? It's just a fraction of red marbles that you draw here with this process, right? It's the number of mistakes it's the fraction of mistakes that you made on the training data. So it's just a fraction of red marbles that you drew with this process where you pick n marbles from the bag. Okay, so that's really the two quantities, right? If we have this marble analogy, right? So what we're trying to prove is that the in-sample error being the fraction of red marbles in the sample should be close to the outer sample error, which is the probability of actually drawing a red marble. Right? And it seems natural that these two should be the same, right? If there's a probability of drawing a red marble and there's a fraction of red marbles that you actually drew in your training example. Of course, it seems natural these two should get close, and they should get closer and closer the more training data you have. Right? Here's just a different analogy just to get going here, right? So another way of looking at it is that right, if you're looking at what is the in-sample error or generating the training data, you could also think of it as you're tossing a coin n times, and each of the times, right, there's a probability of e outs of getting a heads, right? So E out is just the probability of making a mistake, and a heads on the coin would be what corresponds to a mistake. Right, and then basically what we're asking here is, I did n coin tosses of a biased coin. The in-sample error will be the fraction of heads that I got while I was tossing it. Right? It's just the same as drawing these marbles. How many red ones did I get? Here's how large a fraction of heads did I get when I was tossing my coin. And the out-of-sample error is just the probability of getting a heads on one coin toss. Basically, we were interested in understanding how closely concentrated is the fraction of heads that you get to the true probability of getting a heads. Right. And clearly, right, if you look at this is a very well-studied data distribution. What we have over here is just what we call a binomial distribution, where we have n tosses with success probability E out, right, the out-of-sample error, right? We just independently n times flipping a coin that comes up heads with probability E out. And then we're looking at the fraction of this, so we're dividing by n, right? So this is the binomial distribution divided by n. This is a very well-studied distribution, and this actually, so there are plenty of theorems and concentration inequalities we can use in order to relate this fraction of heads that we get to the actual probability of getting a heads. And so this is super well-studied, and one of the most fundamental inequalities here that we will make use of is what's called Hoeffding's inequality. Right, and it says the following. Right, so the Hoeffding's inequality relates the in-sample error and the out-of-sample error to each other. And what it says is that the chance that these two are further apart than epsilon. So epsilon is any parameter you can put into this inequality. So what it says is the probability that the in-sample error and out-of-sample error, meaning the fraction of heads amongst the n tosses and the probability of getting a heads, the probability that these two are further apart than epsilon is at most this expression here on the right. So what does it say? There's a factor 2, and then there's an e to the minus 2 epsilon squared n. Right, so if we look at this expression here, right, it goes down exponentially fast in n, right? So the more coins you have, meaning the more training examples you have, the chance that these two are far apart goes down exponentially fast. On the other hand, right, the precision that you want is epsilon, right? If you want a very fine precision, then you need many more coin tosses. So let's just try to evaluate it on a few concrete numbers just to try and get used to this Hoeffding's inequality. Right. Let's do some examples. So first of all, let's say I have n training examples, right? Then I could ask, okay, what is the chance that the in-sample error and out-of-sample error are more than 10% apart? Okay, so I choose epsilon being 0.1. I can insert it here. I have a factor 2. I have an e to the minus. I have a 2. Epsilon squared is, I guess, 1 over 100. And n is 10. So I get something like minus 0.2. This whole expression is something like 1.64. Right? So this is really a useless statement. It's saying that the probability that they're further apart than 10% is less than 1.64. But any probability is at most 1. Right? So this is a void statement. It doesn't say anything. So maybe this is just too much to hope for that the in-sample error and out-of-sample error are going to be within 10% if you only have 10 training examples. Right? On the other hand, if you settle for something slightly weaker, you say, okay, what's the chance that the in-sample error and out-of-sample error are within 50% of each other, or more generally, what is the chance that they're more than 50% apart? Then you can plug in again. You have the 2, you have the e to the minus 2. The epsilon now is a half, so we have a half squared. Right, so that's a quarter. That cancels out with the 2, so then there's only a half times n. N is 10, so this is e to the minus 5. So if you evaluate 2 times e to the minus 5, this is basically evaluates to like 1%, right? So the chance that the in-sample error and out-of-sample error are more than 50% apart is only 1%. So this is now saying something useful, right? They're about the difference between the in-sample error and out-of-sample error. This was only with 10 training examples, right? Of course, it gets better the more data you have. So let's try to say that, let's say I had 1,000 data elements. Then we can look at the first statement here again, and now it actually is meaningful, right? So we can look at what is the chance that the in-sample error and out-of-sample error are more than 0.1 apart. And basically, we just have to plug it in to this formula up here, right? In place of n, we put 1,000. And okay, if we're a little quick here, we'll notice that this is just 100 times bigger than the n we plugged in before. So the exponent here just becomes 100 times bigger. So instead of minus 0.2, it's minus 20. So 2 times e to the minus 20, that's basically 1/4 billion. Right? So if I have 1,000 elements, then the chance that the in-sample error and out-of-sample error are more than 10% apart is some less than 1/a billion. Right? So this is super unlikely that they're more than 10% apart. Right? So this is basically what something like this can give us. Now, we could, of course, ask, oh, what if I then want a finer precision? What if I want them to be within 1% of each other, the in-sample error and out-of-sample error? Then the issue is, right, that this epsilon squares up here. So this number here, right, 1/100, you square it, it's 1/10,000. Basically, you end up with this void expression again, that the probability that is greater than 1, right? So in here, it's not really, so 1,000 example is enough to guarantee with overwhelming probability that the in-sample error and out-of-sample error are within 10%, but it's not enough to guarantee that they're within 1%. Okay. Finally, you can look at what if I had 1 million data items, and then you could even get a guarantee down to saying that the in-sample error and out-of-sample error are within 0.001 of each other. And if you evaluate it, you'll get something that's actually a reasonable, the chance that they're more apart than this is something like only 27% at most. Right? So there's actually a good chance that they're within 0.001. So clearly, right, the more data you have, the more you can trust that the in-sample error and out-of-sample error are close. Right. So basically one can think of again if this probably approximately correct, right? So approximately correct refers to the fact that the in-sample or an out-of-sample error are at most epsilon apart with good probability, right? So that's the approximately. There's this epsilon difference between them. The probably means that it's only true that they are close to each other almost all the time, right? There's some small chance over here that they're actually further apart than this epsilon. And this is the probably approximately correct. Right, so basically, if we have just a single hypothesis H, right, if there's only one hypothesis in our hypothesis set, then this Hoeffding's inequality tells us that when I get a training set of n training examples, the probability that the in-sample error of this hypothesis is further away than from the out-sample error than epsilon is no more than something that's exponentially small in epsilon squared n. Good. So this really means that if I have a lot of training examples, then it's super likely that the in-sample error and out-of-sample error are close, right? So this really speaks in favor of gathering a lot of training data, right? And the randomness here in the highly likely, so this is the thing on the right-hand side here, is really over the training data set, right? Of course, right, you could ask yourself, when you're actually training a machine learning model in real life, you don't have a random process where you can pull data items from it, right? You just have a data set that you've gathered, right? So of course, this theory has to somehow translate into something reasonable in practice. And I guess the interpretation that would make sense is that, well, if we assume that our data was actually collected in this way as independent identity distributed samples from some unknown data distribution, then it would be highly likely that the in-sample error and out-sample error are close. So really what this theory, in one sense, what we can use it for in practice is to give us some guidelines on what we should expect to be true, right? This theory is telling us, regardless of whether this is a true assumption or not, that our data was collected as independent samples from an unknown distribution, at least the theory is justifying why it makes sense to try and minimize the out-of-sample error and then hope that it carries over to the, minimize the in-sample error and hope that it carries over to the out-of-sample error, right? And it's really basically, as we also saw before, with all these caveats, it's kind of the best theoretical statement we can hope to prove, right? So it's the best justification we can give. Now, shortly in the next video, we'll try to look at what happens when we have more than one hypothesis, right? Because this is a trivial setup and there's really no learning going on when there's just a single hypothesis.